All right. Good morning, everybody. It's 10:02. For those that weren't here on Monday, I posted the video, but basically I was reminding everybody about the AP exam. It's the intention of the College Board to have you take the May test so that if something falls apart and on your end or their end, you aren't able to finish and complete it and submit it properly, you have the June date as a backup. That's, I believe, what their, it's what, from what my understanding is, that's kind of their, uh-oh, my whole screen just went out. All right, I don't know if everyone can still hear me or not right now. My entire computer screen is now black. So let's see. Okay, all right, I'm back. I'm not sure what the heck that was. Okay, looks like everything's still functional. Hopefully I'm still heard. All right, yeah, so they expect is the wrong word. Their intention was May as your date. The June date is back up in case something happens. Do you have the opportunity to just say, nope, I'm just going to go June and go all in and eggs in one basket kind of a deal? Yes, you do. But that's what the reason for the two dates. So with that, we have week 5.3 or lesson 5.1 this week, which is getting us into the math behind magnetism. Remember, take your time doing any of those things, so don't worry about any deadlines when it comes to the UT assignment that goes with that. But there is a Google form attendance type questionnaire for you to check out regarding magnetism. So there are narrated notes. It's up to you if you want to use them or not. I think, if memory serves me, I went through slide 25 for narration. So slides 2 through 25. Slide 1 is a slide that has all the final equations on it. So basically everything up until magnetic fields, even though fields are still a part of what we're doing right now, pushing magnets around. The cause of fields, the source of a field, is going to be for later. So through slide 25. So if you're looking at the notes by yourself, slide 25 is the last one that I had gotten to. And then if you want to go and watch any of the video, I think it was about 50 minutes long going through everything. So you can check that out. There's the first right-hand rule and there's the third right-hand rule, and that only comes with practice. I put a bunch of last year's physics assignments on there where it was just repetition of first right-hand rule. First right-hand rule is when you have curved fingers and you are trying to figure out the magnetic field around a wire. The third right-hand rule is the stop hand, thumb off to the side, fingers up, stop hand. And we did this earlier in the year. So thumb cross fingers equals palm when we're doing our cross product. And that's going to be for the force felt by a particle. So I've got the direction of my particle, fingers field, palm push. So I've got my three components there. And so with that, also last week on Monday, we talked about, let's see, I believe it was review assignment number 6, question 3, and I believe it was review assignment number 8, question number 1. And I do have a way to double check that. Let's see. Yes, number 3 on review 6 and number 1 on review 8. So if you have questions on those specifically, we've got them on the previous day's Zoom meeting. So with that, open up to any questions you folks may have. A couple of days of lousy weather expected, so might be a couple of good days to get a bunch of work done, especially if you took yesterday off and enjoyed the sun, which you should have. Saturday is supposed to be almost 70 and sun. I have a question on number 11 from review assignment 7. Let me open that one up. Review assignment 7. Question number 11. Okay. All right, so it appears that this particular question that we are looking at is a multiple part question. So in looking at what we have a solid conducting sphere. So the center is a conductor, conducting shell. So everything we're looking at in green on my screen is a conductor. We've got a radius and a charge. Let's see here. So radius and a charge, and then we've got inner and outer radius, net charge. We've got inner and outer charge called Q2 prime and Q2 double prime. Okay, so find the charge Q2. So if we look at question 9 leading up to question 11, so if everyone's looking at this one, question number 9, knowing the concepts behind everything, question number 9 should be quick and it should be easy, because we know that if we were to do a Gaussian surface inside this green ring, inside has to have a net charge of 0, which means if I've got a -3 picocoulomb here, I should have a +3 here. And if I have a +3 with a total of +24, that means I should have +21 left on Q2 double prime. And so I see my answer here, 21.1. So that should be a quick and easy one. And if you don't remember that concept, you go through and do Gauss's law and the math would work out. But so recognizing something in terms of we've already put in the time and the effort to understand what charge to expect on Q2 prime and double prime. So a question like that would be one that we would hope would be a quick one. Question number 10, find the magnitude of the electric field at point P. Okay, so for that one right there, what we're going to do is we are going to simply look at it as, I'm probably just going to go with a Coulomb's law, because I have a I have a spherical charge here which acts like a point charge. I've got a distance. Let's see, do we have a distance? Find the magnitude, midway. Okay, so I can do the math and figure out a distance away from the center. And then I've got my my charge there. And so I'm just going to go with Coulomb's law. Gauss's law is just as easy, and it produces the same result. And remember, we can do that because this right here is uniform throughout. So shielding suggests that we're going to get 0 net effect from that. And now the question was actually about number 11. Find the potential at point, find the potential VP at point P. Assume the potential at infinity is 0. Okay, so what we're going to do is we are going to start an integration. We're going to go from P out to inner radius, out to outer radius out to infinity. So we're going to integrate from P to infinity, because infinity is the only place where we have a known value for our potential. That's going to be 0. So in looking at that, we've got our integration of E dot dr. And if you remember the work that we had done in the past, we went from P out to infinity, and then we broke it up into pieces. So going from point P out to, do they give them different names, R1, R2? No, okay, I'm going to call inner radius R2, and then we're going to go from R2 out to R3, and then we're going to go from R3 out to infinity. So this right here, I don't know how big my face is on your screen, but that right there is what we're going to start with. I'm going from, as you can see, I'm going from P out to R2, R2 out to R3, R3 out to infinity. So that's how I get from P out to infinity. I got to go through 3 different regions. And one thing I know is that when I go through this region right here from R2 out to R3, I'm going through the inside of a conductor, because of the charge distribution on the surfaces, I end up with 0 electric field on the inside. 0 electric field means I get 0 change in my potential. So that means that this term right here is going to be 0. So big old X there, cross that one out. So all I have to worry about is going from P to R2 and then from R3 out to infinity. At infinity, we know we have 0. And so what I'm going to do next is integration from P to R2. And so our electric field is going to be K Q over R squared dr. We'll do the same thing here. So I'm doing the same integration both times. We do have an equation for our potential that we could throw in there, but it actually comes out to, when we do the integration, that's exactly what we get. So we integrate and we end up with, whoops, let's see here, mistake there. So we're going to end up with, let's see, bring up the K. Okay. Okay, Q, and let's do this. And then we got this here, so we're going from okay. So now what we have, where do I have it? All right, so what I've got there is my equation there in the middle. So top line, middle line, bottom line. Middle line shows my equation for an, here we are right there, for an electric field. And I'm going to go again from P to R2 and then R3 out to infinity. And so when I do that, K and Q are going to be constants brought out. So K, Q, I snuck in a little Q1 here because this is going to be the electric field for anything that would be inside that point P distance, which means that only charge number 1 on my screen, -3 picocoulombs. So that's going to be my charge that's going to be inside there, that electric field. I've got my negative, because when I integrate R to the -2 power, I bump it up to a -1 and divide by -1. So I get 1 over R negative. So I've got -1 over R minus -1 over R, and over here I do the same thing. Over here, my charge is going to be, again, the charge that's going to be enclosed. I put in a little T right there for total. It's my total amount of charge that's inside that Gaussian surface. So it's going to be the sum total of 24.1 and that -3. Conveniently, that's actually the answer for number 9, because the inner surface and the sphere in the middle cancel each other out. And so I get -1 over infinity. Well, that's just going to be a 0 minus -1 over R3. And so that's how I'm going to go through and do that one there. So in looking at this, if I were to try and graph this, what I would see, and I'll use my cursor here, is if I'm out here at infinity, and actually, you know what, let's start here at infinity. So if I was looking at a first quadrant type graph, out here I'm at 0. And what I'm doing is I am going towards an overall positive scenario. If it's overall positive, that means that my positive test charge, if I had one, is going to be forced to go that way. So that means I'm going to gain potential. So I'm going to see a graph that is going to the tail end of a 1 over R graph. So it's going to be going up and up and up and up and up and up, curving up. Once I get to where R3 is right here, my graph levels off, because this is a potential graph. So my graph levels off, there is no change. Now as I start to work my way in, now I'm starting to go towards a negative. My graph would actually start to drop a little bit, but I'm still going to be at a positive value. So that was number 11 for review question 7. So we actually did 9, 10, and 11. That worked for everybody that was interested. Any other questions? Number 4 on review 3. Okay. Review 3. Question number 4. Review 3. Question number 4. So we've got a picture down here in a second, but we have the radius of our curve. We have the mass of a car given in megagrams, which is weird. We have a speed, which we can convert into meters per second. And we are going to we're going to go without friction to keep it from slipping. At what angle should it be banked? Okay, so in looking at this one, so since we're not going to slide up, since we're not going to slide down, there is no friction. So we're assuming that we're trying to figure out what angle we're without a need for friction. So I start off with that, put in my components. So I've got that. I've got that. Okay, so to start, what I have here, and I can't see my face on there anymore, but whatever. So what I have here is a force diagram that has my normal force and my gravity, and because I'm not sliding up or down the ramp, I'm not going to break it up into components that are parallel and perpendicular. Instead, I'm going to basically say, you know what, if this thing is staying in a circle, that means that the net force holding it in a circle is horizontal, which means the vertical has to cancel. So I'm going to leave it just like that, and as you can see, what I've done is I've taken my normal force and I've broken up into Fy. And instead of calling it Fx, I just simply call it Fc. That's my centripetal force right there. So I can figure out what my centripetal force is going to be, mv squared over r. I'm given all 3 of those values just in improper units. So once I find that, I know how big Fy has to be. It's got to be as big as mg. So the last question is, which angle is going to correspond to the angle of my ramp? And so in looking at this, I'm going to draw a picture of my ramp. Angle theta is what we're looking for. I have, this is my normal here. Is my triangle. Alternate interior angles puts theta right there, which means that this is going to be alpha, which is going to be a complement, which means this is going to be angle theta right there. And so I end up with, that way I can make sure I can see myself here. So now I end up with this as my picture. There's angle theta that I want. Alternate interior angles puts theta right there. This is my Fy, there is my Fc. So it looks like if I find in my picture this top angle, that should be the angle of my ramp. And if we think about this, if I start to make this angle approach 0, if I start to take this angle and really lower it, as this thing starts to approach 0, this angle is going to approach 0, and all of my normal force and all of my Fy force, they're going to be the same. So I can see that this theta and this theta up here, I can see that they match. So if you were doing that one and you got all the right numbers here for the Fy and the Fc and all that. It's just a matter of picking out the correct angle. And so a nice geometry type picture, nice and big so you can see which angles are which, will help you figure out which angle to go with. Because it's really easy to solve and get the complement and put that wrong one in, of course. So, so that was a question on number 4 from review number 3. There's a question primarily about which angle should I be using. So we've got that. All right. Let's see. So yeah, so that's it right there. Better picture for the video. Other questions? So I'll post those. I'll make the video. Can I go over number 3 on review 8? Indeed. All right, so let's open up review 8, question 3. All right. Let's find some paper to write on here. Some fresh paper. All right, so review 8, we had a question on number 3. All right, so we have a capacitance given is charged to a potential difference of, so I have C given, I have my potential V given. The wires connecting the capacitor to the battery are then disconnected from the battery and then connected across a second initially uncharged capacitor. The potential difference across, all right, let me visualize here. Okay, the wires connect the capacitor to the battery. Oh, okay, so we are taking a capacitor that is charged and we are connecting it to a second capacitor, which according to this was initially uncharged. The potential difference across the 6 turns into 4. So I'm going to call this C1, V1. I'm going to call this one C1, C2, and I've got V2. So the key to this one, and again, hopefully you can actually see, I know the screen's probably kind of small, so actually let's do, let's see, what is the capacitance of the second one? So I think we're done there, so I can go back to this so that hopefully it's bigger if you need it bigger. So what I have right here is C1 is going to be the capacitance given, V1 is going to be the voltage given. And so basically I know what my voltage was here, so I can figure out the amount of charge, QVC, I can figure out, I can solve, I'm going to call it Q1. So I can do that right out of the gate. Now, once I disconnect from the battery, I've got nothing else pushing back and pushing charges around. The charges I have are stranded and stuck on their respective plates, which means that unless I have another charge source, a battery or a charge capacitor, that's going to be the total charge that I have to have for the remainder of the problem. I don't get any more than that. So I've got that. I connect it. The key to this one is remembering that when I have 2 capacitors connected all by themselves, they behave as a parallel system. Take a look. The top plate here and here are connected. They act like one big plate. So essentially, I just have one big capacitor now with a big plate on top and a big plate down below. It says that we have C1, I know what that is, mine happened to be 6, but yours could be whatever, of course. And then they give me a new voltage. They said my voltage went from 12 down to 4. So regardless of what the number is, this V2 is going to be the voltage drop or the difference between these two plates. Since this plate is connected through metal and this plate is connected through metal, I'm going to have the same exact voltage over here. So I can add that in if I wanted to. I could add in a V2 right there. So there's a start. I got V2. Because if I want to find C, I'm going to need to use the QVC equation, which means I need Q and I need V. I know what V is. V is an easy automatic. So for my question, it's going to be 4. To figure out what my charge is, I am going to figure out Q1 prime. Q1 prime is going to be right here. That's going to be the new amount of charge that I have on this plate. I had Q1, but in allowing those charges to spread out over onto these plates, the amount of charge on this individual capacitor is going to drop. So Q1 prime is going to be smaller than Q1. I'm going to call this one over here Q2. I'll go with prime. And I know that Q1 at the very beginning was the total. I can't lose or gain any more charge because I'm not connecting to any more charge sources. So now I can go with right here. I can look at that and say, all right, I know what Q1 was from the very beginning. I know what Q1 prime is now. And so Q2 prime has to be the remainder of that. So I now have Q, I now have V, and I've got the QVC equation to figure out what my second capacitance will be. And so that was question number 3 on review number 8. I have a question on problem 8 on review 7. Okay, review number 7 I already have opened up, I think. Question 8 on review 7 there. Is that right there? Okay. So this is review number 7, question number 8. So we are right here, an electric field pointing in the positive X direction, has a magnitude that increases linearly with X as described by the function of E equals BX, where B is 4. Find the potential difference between the points of 1 and 3. All right, so my electric field is pointing in the positive direction. So it's pointing to the right, which means as I go to the right, I'm going from, in my question, I'm going from 1 to 3. So as I go from 1 to 3, I recognize that I'm going to be going with the field. If I go with a field, I'm going to be going with the direction of a positive test charge, so to speak. Anytime I go with the field, it's a loss in potential, just like it's a loss in potential energy when I let a tennis ball move with the gravitational field down. That's a loss of potential energy. So for our positive test charge, which is how we define all voltages, I'm going to get a drop. I'm going to get a loss. And because they're telling us the direction here, so I know my answer should be a negative. So now all I need to do is figure out what the value is going to be. I can go with V equals E times distance if my electric field is a constant, and it is not a constant. So I'm going to have to do an integration. So I'm going to have to go from 1 to 3. I have my E dot dr. In this case, r is my distance. We are moving in the horizontal, where we're analyzing the horizontal. So I'm going to turn that into a dx because that's the direction that matters. And so I end up with, going from 1 to 3, my electric field function of bx dx. So I am going to, from 1, whoops, did that same thing last time. Haven't done enough integration lately. So I'm going to have a 1/2 bx squared going from 1 to 3. So here we go. So I end up with this right here. So I have my equation. And again, I'm trying to figure out what the value is. I already know what the sign's going to be. So I come down here, Vx is my function. I've got, if I do this, I can see through the paper easily. Let's do this the right way there. There we go. So now I've got my equation here. That is the function for my electric field. And so I simply integrated. So increase the value of 2 and divide, I get 1/2 Bx squared. So I had B was 4. I'm going from 1 to 3. So I've got 3 squared is 9 times half of 4. So I've got 18. And I subtract away 4 times 1/2 times 1. 18 minus 2 gives me 16. I already know that the answer is negative because of the direction they told me. And so I know the magnitude is now 16. If I went from 3 to 1, positive 16. So that's question number 8 on review 7. Any others? Getting a lot of them done here. That's good.